Hi. So in this video, we are going to look at some typical questions which you might not be able to see elsewhere. And one of them we'll start off with is the reduction formula for in. And in is integral of dx by this a plus b cos x whole power n, or dx by a plus b sin x whole power n. So this is a special integral, and we need to learn about a specific technique that helps us solve this one. So let's work with an example. So let's suppose when we take the case where n is equal to 2, right? So what we have to find out is I of 2, which is, let's say, integral dx by a plus b cos x. Let's work with this one. Both the cases will be similar. So we are trying to get the formula for this I2, right? So how do we go about this? So the trick here is to put a variable p is equal to, I will put the derivative of cos is sine minus sine, but don't care about the minus here, sine x by a plus b cos x. So this is what I'm going to put here. P is equal to this. Actually, like before we solve this, actually, we should look at I1. And I1 is what? I1 is integral of dx by a plus b cos x. That's it, right? So for I1, we'll connect I1 by p. P is equal to sine x by a plus b cos x. And what we will do is differentiate p. On differentiating p, you will realize what happens is you get a connection between I1 and I2. Okay. So let's see what happens. Differentiation of p will become cos x a plus b cos x. I'm doing it by quotient rule, minus sin x into b into minus sin x divided by a plus b cos x whole square, right? So this expression now becomes cos x into a plus b cos x plus b sin square x. So plus b into sin square x can be written as 1 minus cos square x, 1 minus cos square x divided by a plus b cos x whole square. Correct. This is the expression. So if we simplify this a little bit, I will just rub off this part. Okay, 1 second. I'll just remove this part here. You are getting dp by dx is becoming dp by dx is becoming a cos x plus a cos x plus b cos square x minus b cos square x, which cancels. You have a cos x plus b by a plus b cos x whole square, right? So this expression, now we can write it in terms of, the numerator can be written in terms of a plus b cos x, because we can just add and subtract constants which make that happen. So you can write this as dp by dx is equal to b minus a square by b plus a by b into a plus b cos x. Why am I doing this? Because denominator is a plus b cos x. So notice that the numerator, if you multiply it out, this is plus a square by b. So therefore I added minus a square by b. And this is plus ab by b. So a cos x plus a cos x, which is what I had here. And there is a b, right? So now this becomes dp by dx is equal to, now you have b minus a square by b minus a square by b divided by a plus b cos x whole square, and plus a by b and divided by a plus b cos x, right? because one time a plus b cos x got cancelled from the denominator, right? So you have basically a by b, 1 by a plus b cos x, minus this. I'll simplify. This will become minus a square minus b square by b, a plus b sin x by a square minus b square by b, 1 by a plus b cos x whole square, right? So this is my dp by dx, right? Now, if I integrate now at this stage, what I will get is integral of this should be equal to a by b. Integral of this is I1 minus a square minus b square by b. Integral of this is I2, right? And what is the integral of dp by dx? Should be p, because first we started off with p and differentiated that. So p is basically sin x by a plus b cos x, and that is equal to a by b I1 minus a square minus b square by b I2, right? Now, our job was to find I2, right? I2 was integral of dx by a plus b cos x whole square, right? I1 was a doable integral. I1 was dx by a plus b cos x, right? Why is this doable? Here we can take cos x is equal to 1 minus tan x by 2 by 1 plus tan square x by 2. And this is totally doable. You'll take tan x by 2 is equal to t in the next step, right? So we have an unknown integral I2, which is a square minus b square by b into I2 is equal to a by b I1 minus sin x by a plus b cos x. And this is the formula that we get for I2, right? So the idea here was connect. You have to find I2 and a formula for that. And we took I1 and wrote P. P was what? Instead of cos x, we wrote differentiation of cos x on top and wrote the same denominator, right? And we did dp by dx and got this. And from here, we integrated back to get the original thing, right? So I will show you what happens in the general case. In the general case, let's say you have to find the reduction formula for In, which is equal to dx by a plus b cos x power n, right? Now again, I will start off with the in minus 1. In minus 1 integral is dx by a plus b cos x power n minus 1. And I will construct my p to be differentiation of this cos x is sin x by a plus b cos x power n minus 1. And then I will look at dp by dx. What is dp by dx? It will be cos x multiplied by a plus b cos x power n minus 1 minus sin x, and differentiation of this will be n minus 1 a plus b cos x power n minus 2 and minus sin x, right? Minus sin x into b actually, divided by a plus b cos x power n minus 1 whole square. So 2n minus 2, right? If you simplify this a little bit, what you will get is dp by dx will be equal to, on top you can just have a cos x, cos x into, let's keep it like this, a plus b cos x power n minus 1. And what happens here is minus minus becomes a plus, this plus sine square x, right? So we'll say plus 1 minus cos square x multiplied by b into n minus 1 into a plus b cos x power n minus 2, right? Now this is coming, I have not missed anything here, yeah, and a plus b cos x power 2n minus 2 here. So I can cancel n minus 2 factor here, n plus n minus 2, so this will become n, and this will become just one, a plus b cos x, right? So what I will get, basically I'm dividing by a plus b cos x power n minus 2 up and down, right? So I'll get a cos x plus b cos square x, and this goes away. So you have plus b into n minus 1 minus b into n minus 1 cos square x, right? Divided by a plus b cos x power n, right? So minus bn, you will get eventually something like this. You have to simplify it a little bit, and what you will get is eventually dp by dx will become something like this: cos x into a plus b cos x no, not cos x into a plus b cos x. This was what I wrote earlier only. So this was the previous step. This was a plus b cos x plus n minus 1 into b into 1 minus cos square x. This was the earlier step, divided by a plus b cos x power n, right? I want to write the top part as some constant plus some constant multiplied by a plus b cos x plus some constant multiplied by a plus b cos x whole square, right? This is what how I want to write the top part, and the bottom part can stay as it is. So here I just want to find a, b, and c, which can be found by actually just solving, simplifying each expression and comparing coefficients, right? So you can take constant coefficient that comes here will be n minus 1 into b, right? N minus 1 into b. And that constant coefficient comes from this multiplication. And the constant coefficient here will be capital A plus BA plus CA square, right? The coefficient that comes with the cos x will be A in this side and nothing else. A should be equal to, the coefficient that comes with the cos x will be BB plus 2CAB, right? And the coefficient that comes with cos square x here will be CB square. On this side, it will be 2 minus n into B, and on this side, it will be C into B square, right? So there are three equations, and from this, we can find out our A, B, and C. Let's suppose we have found those A, B, and C. Then you can just separate it out. Your dp by dx becomes basically a into in plus b into I of n minus 1 plus c into I of n minus 2, right? And integrate this, correct? Only after integration you will get in. Right now you just have 1 by a plus b cos x whole power n. After integration you will get this expression, and this will be just p is equal to ain plus bin minus 1 plus cin minus 2. So you have a reduction formula now, right? So you can slowly like reduce, you can say in terms of in minus 1 and in minus 2, right? Because p is known, p was sin x by a plus b cos x whole power n. And similarly, you can go down further. So this is a special trick where whenever you have say I5 integral of dx by a plus b cos x whole power 5, what will I do? I will say I4 was what? Integral of a plus b cos x whole power 4 dx. And I will define the p to be sin x by a plus b cos x whole power 4. And I will do dp by dx. dp by dx, I'll calculate that and I'll try to write that in terms of a plus b cos x, some constant plus b times this plus c times this, and divided by a plus b cos x power 4 and stuff. And once you do this, write the integral, you will be able to connect your I5 to your I4 and I3, then work backwards. I4 will be connected to I3 and I2, and I2 we already found. We found already, right? In the example that I showed before. So this type of thing where you are taking a new function that is related to the integral and you are differentiating it to find a connection between the old and the new integrals is something that is useful sometimes in solving difficult integrals. We will see a few more examples in the coming videos when we will do similar things to derive formulas for integrals. So that's it for this video. Uh, I'll come back with more videos on reduction formulas. See you next time.